Okay, well, welcome to part 3 of 8.8. All right, so I got to thinking in this last problem in our last video, is my area pi over 2? I mean, it's been working so far, but I mean, negative infinity to infinity. Holy cow. So I went to my calculator and I typed in pi over 2. It's 1.570796327. And then I went to y equals and I entered this original function. So I got that in. Then I went to the window. Now, because this did converge, that means our graph has to be really, really close to the x-axis. So we're actually measuring area. So I changed my zoom 6 window. I changed my y min to -1, y max to 1, and I counted by 0.25. And I graphed it. And sure enough, we have space to find the area, and it's getting really, really close to the x-axis. So second trace, let's find the area under the curve, number 7. And let's go from -10, our x min, and to a +10, our x max. And yeah, there it goes. And there we have, holy moly, 1.570. Dang, second quit. 1.57079. We were really close. Okay, let's change it up. Let's go -100. Let's get, if you will, closer to infinity. All right, regraph it. Second trace, number 7, -100 to 100, and enter. Yep, there it goes. Wait a minute, 1.5707963. 07963. 0796. Holy cow. That's the area under my curve. So yeah, if it so far looks like if it's converging all the time, that's the area under our curve. All right, so now we're going to look at our type 2 improper integral. This one's a little bit different. So here, if f is continuous on, it's not closed. B is open. Okay, so it's open because B, it says, is discontinuous. Okay, well, that makes sense. Then if you take and try to find the integral, now we're going to have to put t in for b because that's where we're discontinuous. And now, but we have to take our limit as b approaches from the left side of b. So if we're saying that this is some kind of vertical asymptote, you have to approach b from the left, not from the right, only from the left. And for part B, now we're saying A is discontinuous. All right, but everything between A to B and including B were continuous. So here's, for example, here in this graph, here's A. It's possibly a vertical asymptote here. But now when we take the limit for our t approaches A, we can only approach it from the right. We can't go outside of our lower bound, or as we said earlier, our upper bound. And the other improper integral here would be, again, if we have some value c where in between a and b is my vertical asymptote. So again, if the limit does exist in each of these cases, if the limit exists, then we call it convergent. If the limit doesn't exist, it's divergent. So this one we'll have to check to see if our area, if it converges in the value we come up with, we get a constant. Is that truly going to be my area? All right, so again here, with C being in the middle, we're going to have to break it up into two parts. Lower bound A to C, and then from C to B. We'll break it up that way, and then we'll take the limit as we approach C. For this one will be from the coming in to the on the right side, or excuse me, left side, and over here we're coming in from the right side. So let's take an example of one of these. So let's say we want to integrate from 0 to 5 of 1 over x squared dx. All right, so there is a vertical asymptote at 0. The limit as x approaches 0 of 1 over x squared equals infinity. It's discontinuous. So we're going to change this to the limit as t approaches 0 from the right side only. Integrate it from t to 5, 1 over x squared dx. Okay, well, we've integrated this before. That's negative 1 over x to the first power. Upper bound 5, lower bound t. Let's plug it in. So we're going to get that limit as t approaches 0 from the right, negative 1 over 5 plus 1 over t. Well, if this is a constant, don't worry about taking the limit. You can, if you will, factor it out. Well, I can't say factor because we're not multiplying. But the limit as t goes to 0 plus, and this is a constant, there's no t in it, so we're still going to have negative 1/5. This is the one we have to look at. What happens when the limit approaches 0 from the right? So 1 over something getting really, really close to 0. So 1 over t, if I were to graph it, is this curve right here. So as this curve approaches 0, we are heading off to infinity. So negative 1/5 plus infinity, that's divergent. We can't find that area. Example 7. Now let's say we go from 0 to 5, but now it's 1 over the square root of x dx. All right, we have discontinuity here because if you put in the 0, the square root of 0 is 0. So again, that's an undefined value, just like we were up here. That's still technically a vertical asymptote. So if I graph it, there's my picture. Very similar to our 1 over x squared. It's just that we got a little more space here than we did here. So let's change out the 0. Let's call that the t, and we'll take the limit as, again, t approaches 0 from the right side. And we'll call 1 over the square root of x, we'll call that x to the negative 1/2. Okay, so add 1, that's going to be x to the 1/2. Divide by 1/2 is multiplying by 2. And so now we'll substitute things in. So 5, well, let's see, that's the square root of x, so that'll be 2 times the square root of 5 minus 2 times the square root of t. So again, here's this constant value. So you take the limit as t goes to 0 from the right, it's still going to be 2 times the square root of 5. And now here, the square root of 2 times the square root of t, that's this graph right here. So as t now approaches 0 from the right side, I'm approaching that point right there. Only from the right side. There's nothing over here to the left. That's the importance of coming in from the right with your limit. So that is technically approaching a 0. So my answer here is 2 times the square root of 5 minus 0. That's 2 times the square root of 5. So this converges. It's convergent. Okay, example 8. If we want to integrate from 0 to 2 of 1 over the cube root of x minus 1 inside my cube root symbol, dx. Now, okay, wait a minute. 0 and 2 are okay. I can take the cube root of a negative 1 and I can take the cube root of 1. But when x equals 1, that's going to give me a 0 in the denominator. So here's this vertical asymptote here. So we're going to have to break this up at the place where we are discontinuous. So we need 2 separate integrals, from 0 to 1 and then from 1 to 2. So again, we're going to integrate this, but again, once you integrate it, we'll get Be the same for both. So let's see, we'll call this x minus 1 to the negative 1/3 power. And we'll integrate that. So we add 1 to that. That's going to be 2/3. Well, you divide by 2/3. That's multiplied by 3/2 of x minus 1 to the 2/3 power. Then if you take the derivative of the inside, that's a 1. So we don't have to worry about any chain rule here. So that's all good. And now we're going to put in our t's and our zeros, and then our t and our 2 over here. So if we put in our t, that's going to be 3/2 times t minus 1 to the 2/3 power. We put in the 0. 0 minus 1 is negative 1, so negative 1 squared is 1. Then you take the cube root of 1 is 1, so that's just minus 3/2. Over here we plug in the 2. 2 minus 1 is 1, so 1 to any power is 1. So there's this 3/2 minus 3/2 times, put in the t minus 1 to the 2/3 power. Okay, so what do I need to do here is, well, I've created this new function. I need to go to my calculator to see what this picture looks like. So I went to my calculator and I graphed 3/2 times x minus 1, close the parentheses, raised it to the 2/3 power, and I graphed it, and the picture looks something like this. It comes right down to the 1 at the x-axis, hits it, and bounces back up. All right, so as I approach 1 from the left side, coming in this way, my y-coordinate is 0. So all of this becomes 0. And as I approach it from the right, for this limit, this too is approaching 0 as I come in from the right. So this cancels out. So we're going to get negative 3/2 plus 3/2, which gives us a 0. So these two areas are exactly the same. One's below the curve, one's below the x-axis, one's above the x-axis, and negative area and a positive area that are same, they cancel out to a 0. Okay, so that's a real number. It's convergent. All right, example 9. Integrate from 3 to infinity of 1 over x times the square root of x squared minus 9 dx. So here, 3 is going to cause a problem inside the square root. So we have 3 squared is 9 minus 9. This will give me a 0, so we're discontinuous at 3. It's creating a vertical asymptote, and oh great, we're also discontinuous at infinity. So what we have to do is we have to break this into 2 parts, because we have infinity here and it's something that's discontinuous there. So separate it wherever you want. I'm going to say 4. So I'm going to break this down to integrate from 3 to 4 of our function, plus then 4 to infinity of our same function, all with respect to x. Okay, so let's go ahead and take out the 3 and make that a limit as t approaches 3. Integrate from t to 4. And then let's take out infinity over here. Oh, I forgot to change this to a t. Please change that to a t. I hope I did that in the next example. So these look kind of tough, so I'm going to check my integration tables, and sure enough, there's a match right there. So each one of these is going to be 1 over a, secant of the inverse secant of u over a. So let's plug those in. My u is the x, my a is the 3. So it's a straight substitution. Oh good, there's my t right there. I remember to put it there. So the limit as t approaches 3 from the right, let's put in the 4 and we put in the t. Here we'll put in the t and we'll put in the 4. Holy moly, so let's see, 1/3 inverse secant of 4/3 minus 1/3 inverse secant of t over 3. Okay, well, you know what, over here just switch them around. Switch them around the minus sign. Well, wait a minute, hold the phone. I was getting worried about calculating this right here, but I have a positive version and then I'm going to have a minus version, so I don't have to worry about figuring out what those values are. Let's just cancel them out. They're opposites. Okay, inverse secant. Oh, great. Just like that inverse tangent, I need to look at what its graph looks like. So here is the graph of inverse secant of x. So now, as t approaches 3 from the right, so this is going to be really big, and then come down to a 3. So this is getting closer and closer to a 1. Okay, so let's see. As I approach 1, okay, so I could say, let's say 6/3, 5/3, 4/3, 3/3. I'm approaching 1, if you will, from the right once I divide that. So I'm approaching a 0 for all of this right here. This whole, my inverse secant becomes 0, so negative 1/3 times 0 is 0. Over here, now as I put infinity in for this t, okay, now we're heading out this way. So this is infinity over 3, or call it infinity. We're approaching pi over 2. That has to be multiplied by 1/3, is now going to be pi over 6. So we have 0 plus pi over 6 is just pi over 6. And since the limit exists, this is convergent. And that ends our 8.8.